to also put things into a little bit more perspective, the question that you might be wondering is if the changes, the rates of change, or the change in the rates of change aren't constant, is it possible this is an exponential function? Because exponential, we also mentioned this idea of a horizontal asymptote, the fact that if you continue to cut something in half, let's say, that will approach zero but never quite reach it. In theory, right? I could give you a hundred pounds of chocolate, and you can eat half of that every day. Well, maybe not every day, but let's say you eat half of your chocolate every month. Well, you'll actually, in theory, never run out because half of something is something, right? You can't ever cut something in half and not have anything left. So the other thing to consider is that with an exponential function, I do have a vertical intercept. There is no vertical asymptote. My graph would always cut through the vertical axis. The other way we could double check that is to see if there are constant ratios. So in other words, if I took 1.67 divided by 5, that should be the same ratio I would get when I take 0.83. Oh, not, excuse me, I'm taking the wrong values here. If I took 5 divided by 10, well, that's being cut in half, but then notice that 3.33 divided by 5 is not, it's not being cut in half anymore. It's actually, that ratio is getting to be a little bit bigger. They're a little bit closer together, those values. And same thing with, if I do 2.5 divided by 3.33, and again, that's a relationship of about 0.75 to 1. So the ratio is not constant either, and so that we can't necessarily call it an exponential function. So anyway, just a little something to think about. And now let's look at kind of a more conceptual thought process for how we talk about rational functions. We just considered the style or flavor of functions where we have a constant, so I'm going to call c is going to be a constant, divided by x. So we looked at 10 divided by x, and you can probably guess that, and negative 10 divided by x, you can probably guess that a lot of these behave in much the same way. So if it were 20 divided by x, well, the outputs would initially be a little bit higher than 10 divided by x because it would take a lot more to divide 20 than it would to divide 10 in order to get the same output value. So, but anyway, what if we consider something like this? Let's say y equals 10 divided by x squared. And let's just kind of begin thinking about how this behaves. So far we talked a little bit about vertical asymptote and horizontal asymptote. Well, let's think about what the vertical asymptote is here. So vertical asymptote we define as any point at which the input is undefined. So when is this quantity undefined? Well, it's undefined whenever the denominator is 0. That's the only time I'm going to have an issue problem solving. So when is x squared equal to 0? I don't want that to happen, right? Well, the only number that I can multiply by itself and still get 0 is 0. So when x is 0, I still have a vertical asymptote. So I would say that the vertical asymptote is x equals 0. And I'm just going to kind of keep track of some things here and just sort of get a picture of what this might look like. So let me just plot my vertical asymptote. There it is. And this vertical line represents, remember the way to think about this is the x values along this pink line are all 0. So it's this point is 0 something, this point is 0 something. So to describe a vertical line, we often just say, hey, x along this line is always 0. Alright, so now we want to begin thinking about kind of what happens on either side of this asymptote. Well, let me begin kind of by thinking about the signs of value. So where will my graph appear? Will it appear, we noticed that sometimes it appeared above the horizontal axis, like in this region, and we observe where it happens in this region, and similarly, where are these components going to take place? Well, let's try to analyze this without graphing it, just initially to kind of get a sense of what this should look like. So when x is positive, well, 10 divided by a positive number is going to be positive. If you square a positive number, you're going to get a positive. So we know that in this quadrant, I'm going to put a check mark here to say in this quadrant, the first quadrant, that's where I'm going to be able to see my graph. Down here, there's not going to be anything down here because there's no way I can divide 10 by a positive number and get a negative. Similarly, well, in this case, since it's being x is being squared, That means that if I put in a negative number for x, a negative number squared will yield me a positive number, and so a positive divided by a positive is a positive. So again, I should see it over here. Well, let's just kind of think about what these values might look like. So when x is, let's say, -2, -1, 0, 1, 2. Well, I know that when x is 0, y is undefined. And when x is 1, well, 10 divided by the square of 1 is 10 divided by 1, which is 10. And similarly, if I divide 10 by the square of -1, I get 10 divided by 1, which is 10. And as you might guess, 10 divided by 2 squared is 10 divided by 4. And 10 divided by 4 is 2.5. So in comparison to my other graph over here, this guy drops much more rapidly. I shouldn't say much more, but it drops more rapidly, right? Whereas it took an x of 2 to get to 5, y to 5, in this equation, 10 divided by x, it's now taking me to 2.5 instead of to 5. So similarly over here, same thing. If I square -2, I get +2, and I get +2.5. So it's almost like I get something that looks like this, and over here, same thing. It's like a mirror image. And then when x is -1, or sorry, -2, I get 2.5. So it's a quarter of that. It's a quarter of this distance. So that's about a quarter of the distance. And same thing here. So I'm guessing it's going to look something like this. Now again, we want to sort of think about what is going to happen in the long run. And that's going to tell us what our horizontal asymptote is. Well, the long run goes two ways. We have to consider kind of x as it gets bigger and bigger and bigger this way. And as x gets bigger and bigger and bigger this way, what happens to my y values? Well, as you can probably guess, that if I begin dividing 10 by larger and larger numbers, it's going to go to the division of those two will approach 0. So 10 divided by 100 will be closer to 0 than, say, 10 divided by 10. And the x squared is only making it happen faster, right? It goes to, at x is 2, y is 2.5, whereas in the previous problem, x2 corresponded to a y of 5. So it's decreasing very, very quickly. And just to kind of make that comparison, there's -10 divided by x. Let me change that to 10 divided by x. And then I'm going to plot 10 divided by x squared right below that. And I'm also going to come over here to my y2, and I'm going to change the style of my graph. So I'm going to do a solid line. And the way I did that is I just highlighted it and pressed enter. And now I'm going to graph them both together. So there is 10 over x squared, and there is 10 over x. So notice how that drop happened much faster, but it still sort of has the same overall shape. And it kind of looks like, just because the line's bold, that it dips below 0, but that's just kind of a, the pixelation of the screen as to why that's happening. So there we go. That's pretty interesting that's what this graph looks like. So let's now think about what happens to y as x gets bigger. We kind of mentioned that as x gets bigger, and we can kind of go to our table here to visualize this a little bit better. Let me start my table at 0 and maybe go up by hundreds. And in fact, at 0 it's undefined, and very rapidly we see that the y values, as x increases, y drops down to 0. But we could keep going and we'll notice that y never reaches 0. Because again, how big of a number do you need to divide 10 by, or even the square of what number do I divide into 10 in order to get exactly 0? And the answer is you cannot possibly divide 10 into enough pieces to separate it in exactly 0 chunks. So I'm also going to plot this horizontal line here saying, hey, this is the line that represents in each direction, this way too. If I increase x to very, very negative values, I'll still get 10 divided by a very, very large positive, which will be a very, very, very small value, very close to 0 value. And so I would say that the horizontal asymptote is represented by the horizontal line y equals 0. Let's take a look at this example here. This actually deals with using rational functions to model oil spills. And suppose that in this case, this model is actually one that helps model the Exxon Valdez oil spill, which occurred a number of years ago, and in which a lot of oil went into, I think this was the coast of Alaska. Double check on this, but I think it was the coast of Alaska where there was this big oil spill, and so they basically used these different cleanup efforts, including high pressure hot water washing, cold water flushing, fertilizer application and then relocation of oil sediment. So it was a very intense process, and so a model pretty close to this model here, where C of P equals this whole right-hand side, models the cost of cleanup. So C, the output of this, is the cost of cleanup to remove P% of the pollutants. Now here we're dealing with whole numbers. Removing, so if P is 1, then we're talking 1%. If P is 10, that's 10%. And we want to kind of begin understanding this. So we're going to create a table. We're going to ask what happens to cost as the percentage of cleanup approaches 100%. Is it cheaper to clean up at the beginning of the process or once everything is nearly cleaned up? Why do you think this is? So we'll answer a few questions. We might hypothesize that it's going to cost a lot more to clean up the last 1% than it probably will to clean up the first percent. So imagine that you have sort of all this oil spilled into the ocean. So there's your big oil spill, and you're trying to clean this thing up. Well, it's kind of like, you know, after a storm when you're trying to rake the leaves from the yard, you can probably take out big chunks of this fairly easily, but then as you have less and less left over, you know, maybe little spots everywhere, those are going to be a lot more difficult to clean up, and those are going to be kind of more scattered about, and maybe they're going to be so microscopically small that you'll need some special procedures to be able to soak up that oil so it doesn't damage wildlife and it doesn't damage the ocean any further, etc. And then, you know, eventually you just get these really, really small, maybe they're just a couple of rocks that are soaked, or so those cleanup efforts really go far, and it probably gets more and more expensive to do finer and finer cleaning than it does to, you know, grab a big net and take a lot of the junk off the top. So this equation, which we're told the cost is found this way by taking 0.08 times P divided by 100 minus P. Okay, well, let's first of all describe this as a rational function. So why is this a rational function? Well, if I do some rearranging here, this is 0.08 P to the first power. So this is like saying 0.08 x to the first power. And that, by definition, is a polynomial, right? That's actually a linear polynomial. This is a linear function. And same thing down here. 100 minus p, well, that's a polynomial because anytime I see a variable, the variable has an exponent of 1, or it's a positive whole numbered exponent. And this is a linear polynomial as well. So we know that this thing is, by definition, a ratio of two polynomials. It's a division of two polynomial functions. Okay, so we know this thing is a rational, and we'll begin to kind of just analyze. Actually, I'm just going to go ahead and plug this thing into the calculator and look at the table that way. Just to kind of give you an idea of how we calculate with this in case you ever want to do some by hand analysis. So let's say we just want to look at 1%. Well, 1% would just require putting in a 1 for p, and this would give me 0.08 times 1 is 0.08, 100 minus 99, or 100 minus 1 is 99, and then I could do 0.08 divided by 99, and I get a very, very small number in this case. We'll talk more about exactly what that's saying and why that cost is so small, but this is also, keep in mind, in a bigger unit. This is in, I think, let's see, billions of dollars. So if I multiply this by 1 billion, so it's 9 zeros, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's actually that many dollars, $808,000. So that's actually quite a bit of money. And so now, let's if you can also do it this way. You can also put in 0.08 times 1 in parentheses to indicate that that's the numerator. We have extra parentheses here. Divided by parenthesis 100 minus 1. And that tells us that there it is. It's the same cost again. So it's just whether you do it in one step or two. But nonetheless, I'm going to put this into my y equals. I'm going to plot 0.08. Again, put this in parentheses. 0.08x divided by 100 minus x. If you don't put those things in parentheses, then instead your calculator might interpret this as saying 0.08p, divide that by 100, and then subtract p from the entire result. So what we don't want our calculator doing is this. 0.08p divided by 100 minus p. that's going to give us a different result. Because in this case, we want the p to be in the denominator. We want 100 minus that, and not the ratio of these two minus that. So be careful when you enter that in. So let's just look at what would be a practical domain here. Practical domains. Okay, so what would be reasonable values for the input? Well, this is the percent of cleanup. So I would imagine that anywhere between 0 and 100% is probably what we should consider. And then similarly, well, we don't exactly know what the cost is going to be, but we know we can't have a negative cost. And so let's look at, I don't know, I can't imagine how high this is going to get, so let's maybe just leave this at 100 for now and see how this thing behaves. So now I'm just going to kind of look into, oh, I guess we don't really need that because we're not graphing it yet, but let's just sort of look at our table. Let's go from 0, let's start at 0% and go by increments of, I don't know, 5% maybe. All right, so now what are we looking at? Well, we're looking at the percentage of cleanup, and then we're looking at the cost to do that. So if you notice, and a really interesting little feature here is that if you go over to p being 0, notice that now we don't have an undefined, we don't have an error here. Well, why is that? This is still a rational function. 100 minus 0, or 100 minus p is the denominator, right? So a vertical asymptote, p equals 0, does not create an undefined or a 0 in the denominator. It definitely could agree that it's a different value of p that might zero out the denominator, but x equals 0 or p equals 0 is still a valid number. So as we begin to go farther and farther down, 25, 30, 35, 40, 45, 50, notice that the cost is starting to really skyrocket. Now this is in billions of dollars. So by the time you reach 95%, we're up at $1.52 billion. But look at this, only 5% less than that would only cost roughly less than half of $1.52 billion. Cleaning up 90% would correspond with a $0.72 billion cleanup charge. And the more interesting part here is that if you actually go from, let's say, 55 to 60, that increase in dollar amount is only something like $0.03 billion. But going from 85 to 80 to 85% is like maybe $0.13 billion. And going from 90 to 95% is almost like a $0.8 billion more. So what might I imagine this graph to look like? Well, I kind of speculate that based on these increases, that the rate at which these cost cleanups are increasing is that it appeared that up to 100%, this is 100, that sort of the cost really went up by very little bit, and then suddenly the jumps in costs got a lot bigger, so the rates of change increased by more and more and more. And just to verify that, let's take a look at the graph. So again, I set my domain to be from 0 to 100%, and it looks like, well, based on our table, my y's should probably don't need to go above $2 billion because that seems to be my biggest cost value. So I'm going to just change my window here to go from 0 to $2 billion. So I'm going to graph this. And notice that over here, the costs are just so low, our calculator doesn't really display it well, but as we go from left to right, these costs seem to really skyrocket. They seem to really jump as you get closer to 100%. Well, what happens, how much would it cost to actually clean up 100% of the spill? Well, that would be, let's see, C equals 0.08 times 100 over 100 minus 100. And now you begin to kind of do the math here. You say, well, that's 8 divided by, 100 minus 100 is 0. And so it appears that actually when p is equal to 100, we have a vertical asymptote. That value makes an undefined cost. That x value creates an undefined y value. And so p equals 100 is actually a vertical asymptote. And over here, so at p equals 100, we kind of get something like this, that the cost getting closer to p equals 100 rise exorbitantly, but why would it be the case why would it make sense that 100% would have an undefined cost? So 100% cleanup has an undefined cost. Well, how possible do you think it would be to actually clean up 100% of an oil spill? And that's sort of like saying ask yourself, have you ever cleaned up your house to be 100% spotless? Well, the answer is it's almost guaranteed that that's not the case, because there are particles of dust that we can never see, i.e., there are spots of oil that we could probably never clean up because they're so microscopic. And so it would make sense that, the cost, if we wanted to be 99.999% cleaned up, that cost is probably going to be very, very high, but that it's never going to reach a cost of 100%. So anyway, that's sort of one way in which we would see the application of vertical intercepts, is sort of this limiting value. And similarly, if you wanted to kind of mathematically go out and say, well, shouldn't there be something that's happening after that intercept? Well, let's think about this. If we have c equals 0.08p divided by 100 minus p, what happens when p is bigger than 100? Well, when p is bigger than 100, this numerator is positive. But when p is bigger than 100, now I get 100 minus a number that's bigger than 100. So 100 minus, let's say, 101 will make for a negative output value. So that doesn't really make sense. It'll make for a negative cost. And probably based on the way we've seen things, if this proportion is positive over here, my guess would be that we'd see something negative over here. Well, let's check it out. So I'm going to try to change my window here. And I didn't actually realize that we're so far over on this video, so I'm going to stop here and we'll just finish this up in the next